Why are inductive and capacitive reactance so confusing in AC analysis? Imagine trying to understand two opposing forces that both influence how electrical currents behave in a circuit. That's what makes inductive and capacitive reactance tricky to grasp in AC analysis. They seem similar because they both oppose current flow, but their behaviors are quite different. To really get it, let's break down what reactance is. It's the opposition to the flow of alternating current caused by inductors and capacitors. Unlike resistance, reactance doesn't turn electrical energy into heat. Instead, it causes a phase shift between voltage and current. Inductive reactance happens in inductors, which are coils of wire. When AC flows through an inductor, it creates a magnetic field that resists changes in current. The key point is that the higher the frequency of the AC, the stronger the opposition. The formula for inductive reactance is 2 times pi times the frequency times the inductance. This means if the frequency doubles, the reactance doubles too. Inductive reactance causes the current to lag behind the voltage by 90 degrees, making things a bit confusing when you try to analyze the circuit. Capacitive reactance, on the other hand, occurs in capacitors, which store electrical energy in an electric field. The interesting part is that as the frequency increases, the opposition decreases. The formula for capacitive reactance is 1 divided by 2 pi times the frequency times the capacitance. So, if the frequency doubles, the capacitive reactance halves. Capacitive reactance makes the current lead the voltage by 90 degrees, which flips the phase relationship seen in inductors. Now here's where the confusion kicks in. The phase shift is opposite for inductors and capacitors. In an inductive circuit, the current lags behind the voltage, while in a capacitive circuit, the current leads the voltage. This can be confusing because both reactances are frequency-dependent but in opposite ways. When you combine them in a circuit, they can cancel each other out, which adds another layer of complexity. The net reactance is simply the difference between the inductive and capacitive reactances. If they are equal, the circuit acts as if it's purely resistive at that specific frequency. Understanding how reactance changes with frequency is vital for designing circuits. For example, engineers use inductors and capacitors to create filters that block or pass certain frequencies. They also use these components in oscillators and tuning circuits. The key to mastering AC circuit analysis is recognizing that inductive and capacitive reactance are two sides of the same coin but behave very differently as the frequency changes. This difference is what often trips people up, but once you see how they oppose current in opposite ways and how their reactances depend on frequency, it becomes much clearer.